You know how you can see a beautiful rose in a garden, or heck, even just a dandelion that pops up through the pavement, and you notice how fast it all fades? One day, it's this amazing splash of color, and then, poof, it's gone. It feels kind of random, right? Well, it's not.
So let's get right into it. Why can an orchid on your desk last for what feels like forever, while a morning glory is basically done for the day by lunchtime? That's the big question, the mystery we're going to solve in this explainer.
And our guide for all of this is an absolutely classic study from way back in 1985. An ecologist named Richard Primack pulled together data from all over the planet to basically crack the code of how long flowers live. And what he found was so important, it completely changed how we think about the secret lives of plants. Okay, so the first piece of this whole puzzle is all about location, location, location. Seriously, it turns out that where a flower grows has a massive, massive impact on how long it gets to live. This is the big external factor that really sets the stage for everything else. And the first major rule Primack found is actually pretty simple. The colder it is, the longer the flower lasts. See, in warmer places, a plant's metabolism is just running hotter. Everything happens faster. It's why a bouquet of flowers might last for weeks in the winter, but the same kind of flowers will wilt in just a few days in the summer heat. It's basically a live fast, die young strategy, and it's all driven by temperature.
And just look at how dramatic this effect is. In a hot, humid, tropical rainforest, your average flower is around for just over a single day. But move up to the cool Chilean subalpine mountains, and that lifespan jumps to almost 7 days. That's not a small difference. That is a huge gap, all because of the climate.
And it's not just about where you are on the globe either. It's also about the time of year. Primack's data showed that in the very same forest, the flowers that bloom in the cool weather of spring last, on average, almost 3 times longer than the ones that pop up in the blazing heat of late summer.
Okay, so the environment is a huge factor. We get it. But what about the plant's own programming? You know, its genetics. Does its family tree, or its, let's call it a mating strategy, play a role? Oh, you bet it does. This is where the plant's internal blueprint really comes into play.
And this is a perfect example of 2 totally different playbooks. On one side, you've got orchids. They have these incredibly complex, intricate flowers that are often designed for just one specific pollinator. So if that one pollinator is rare, well, the flower has to stay open and just wait, sometimes for weeks. It's a real high-risk, high-reward game. Now, bromeliads, they're playing a different game. They have simpler flowers that pretty much any visitor can pollinate. They get the job done fast, so they don't need to stick around. It's a numbers game.
Now, here's a really cool little wrinkle in all this that gets right into a plant strategy. For species that have separate male and female flowers, what do you think? Do they live for the same amount of time? Well, it turns out the study found an incredibly clear pattern. Out of 17 different species they examined, a whopping 14 of them showed the exact same thing. The female flowers consistently lasted longer than the males. It's not even a contest.
And when you think about it, the evolutionary reason for this is just perfect. A male flower has one job: release its pollen. Once the pollen's out there, its shift is over. It's done. But a female flower, it has to stay open, stay receptive, and wait for that pollen to arrive. Her job takes patience, and her lifespan reflects that completely different pressure. It's a beautiful example of form following function.
All right, so let's bring in the pollinators themselves. You know, the bees, the birds, the butterflies. It seems obvious that the type of pollinator would be a major factor, right? But it turns out the relationship is, well, it's complicated. What Primack discovered was that there just wasn't some simple, easy rule. You couldn't just say, oh, bee-pollinated flowers last X days. The much bigger factor, once again, was the habitat, the environment where that pollination was happening. The environment is the boss.
And this comparison just says it all. Check this out. Both of these groups of flowers are pollinated by birds, but in Australia, they last an average of 12 days. In tropical Puerto Rico, they last just 1 day. Same kind of pollinator, but the environment completely flips the script. It's such a powerful reminder that in nature, context is absolutely everything.
So how do we tie all of this together? We've got the climate, the plant's own strategy, the pollinator. This is where Primack proposed a single, elegant theory that explains everything we've just looked at.
Now, I know this graph looks a little academic, but the idea behind it is actually really simple and really powerful. It says that a flower is basically doing a cost-benefit analysis every single day. It will stay open as long as the potential reward of getting pollinated is greater than the energy cost of just keeping the flower fresh. It's a high-stakes calculation.
And you can break that whole trade-off down into some simple economics. If your pollinators are few and far between, and it takes a lot of energy to build a new flower, like in a cold environment, then it makes sense to maintain the one you've got, keep it open longer. But if pollinators are everywhere, and it's energetically cheap to make a new bloom, the plant just cuts its losses on the old one and opens a fresh one tomorrow. It's pure supply and demand, but for flowers.
So, the next time you see a flower wilting, don't think of it as a sign of failure. It's an active, strategic decision. The plant has literally run the numbers and decided to spend its precious energy somewhere else. Its lifespan isn't passive. It is a calculated evolutionary risk. And Primack himself summed it all up with this amazing line in his paper. He called it a dynamic drama in which the flower longevity determines the length of the performance. It's not a static picture, it's a play, and every single flower has a different runtime. And that's really the legacy of this research. It was a game changer. It forced scientists to start thinking about pollination in 4 dimensions. It wasn't just about the shape and color of a flower anymore. It was about its timing, its duration, its whole performance on the ecological stage. It added the crucial element of time to the entire story.
It really makes you see the natural world differently, doesn't it? Every single flower you see is constantly running this complex, invisible calculation. And it just makes you wonder, what other hidden dramas, what other secret calculations are unfolding all around us, right under our noses?